Scientific notation, the basics. Scientific notation is a number written m times 10 to the nth power. So some number times 10 to a power. Now the number and the power of 10 have some restrictions, so let's talk about those. The number out front times the 10 to a power, that's where 1 is less than or equal to m, which is less than 10. Okay, this is just a fancy math way for saying this just means there's one non-zero digit to the left of the decimal. So before the decimal, like 1.3, 6.57, 8.06324, there's one non-zero digit to the left of the decimal. And I should say just one digit that's not zero. 10 would be one non-zero. You have a 1 and a 0, but it's one digit, and it's to the left, and it's not a 0. All right. So then an n is an integer, so a positive or negative whole number. You don't want to have 10 to the square root of 2 power or 10 to the 1/2 power. It's going to be 10 to the 5th, 10 to the negative 2, 10 to the 23rd. All right. So why do we have scientific notation? Well, and it's called scientific. Right? In science, if you've had a physics class or if you've had a geology class or geography or something, you may have talked. Your teacher may have talked about the mass of the Earth, or the distance the Earth is from the sun, or in physics there's something called Planck's constant. I think it has something like 10 to the negative 26 in it or something. Well, that's better than writing a decimal and 25 zeros every time. So you're talking about really, really big numbers or really, really small numbers, then scientific notation is the way to go. So we're just going to practice a couple of things in this video. We're going to take scientific notation. We're going to start with it. Notice there's one non-zero digit to the left of the decimal here each time, right? So that's my scientific notation. I'm going to practice writing this in decimal notation, which is your standard notation you're used to seeing, okay? It's a standard number without times 10 to a power, that kind of thing. Then we're going to turn around and we're going to take something that's written in decimal notation and say, okay, let's practice writing that in scientific notation. And then finally, we're just going to do 3 problems at the end where we multiply or divide 2 numbers that are in something that at least resembles scientific notation. It may not be because of the number of decimals to the left and that kind of thing, but we want our final answer to be in scientific notation. So, and then that whole one digit to the left that's not 0 of the decimal, then that's going to come into play for sure. So let's look through some of these. Write this in decimal notation. So what I'm going to do, and look, I know people get caught up in, let's move it to the right and to the left and all this other stuff. I don't get caught up in that. I think about what am I doing, right? I'm multiplying 7.89 times 10 to a positive exponent. That's a positive 3. 10 to a positive exponent is big. 10 times 10 times 10, right? You're making this thing bigger. If I'm making it bigger, I'm going to take my 7.89. I'm going to move my decimal this way, right? I'm making it bigger, and I move it 1, 2, 3 places, right? I move it 3 places because it's 10 to the 3rd power, right? Our number system is based on tens, right? You have the ones, the tens, the hundreds, which is 10 times 10. Then you have the thousands, which is 10 times 10 times 10. Then you have the 10,000s, which is 10 to the 4th power. So because our numbers are base 10, that means each time we multiply by 10, we move the decimal 1 place. Well, if it's bigger, we're moving it to the right, but I don't want to get caught up into the right. Which way is bigger? We'll move the decimal out that way to the right. It makes it bigger. So when I go beyond my 9 here and I add another digit, I've got to put a 0 in its place there, right? So that means this is the number 7,890. And put a comma there, right? 7,890. So then what about 3.521 times 10 to the 5th? Again, times 10 to what? A positive exponent, which means what? The number's going to get larger. So we're going to say 3.521. We're going to go 1, 2, 3, 4, and 5 this time, right? The power's 5. I've got to add 2 zeros this time. So now I have the number 352,100. Now notice I didn't put my commas in there yet because I was started at the 3, right? You put your comma every third one. So 1, 2, 3, so you put your comma there, right? So, and then there's no more commas. 352,100 is this number here in decimal notation. Okay, where's the decimal now? The decimal is here, but when the decimal is at the end of a number like that, when it's an integer, we don't write the decimal. We don't put 1 point or 2 point. We just put 1 or 2. If it's 2.7, we have to have the decimal, right? But if there's nothing after it, then we don't put the decimal. We don't put point. So here, 2.07 times 10 to the negative 2. So now when you talk about 10 to a negative, if you remember, a negative exponent means what? Put it in the denominator. Divide by it. Put it in the bottom is the unfancy way to say it, right? That's a good word, unfancy, right? That's a real good word. Okay, I'm a math teacher. So if I say unfancy, you know what I mean. All right, so 2.07 times 10 to the negative 2, that's like dividing by 10 twice. Now you're making your number what? Smaller. When you divide by 10, you're making it smaller. So here, we're going to say 2.07, and we're going to move the decimal place 2 places, but this time make it smaller. So 1, 2. There's a 0, and here's your new decimal, and that decimal is non-negotiable. You have to have it. So now you have 0.0207, and that's your answer here, all right? Now, the other way you could write this is 0.0207. The only difference is I put this 0 out front, and here I didn't put it, okay? But notice 0207 follows the decimal. You can put the 0 in front of the decimal, the left of the decimal if you want to or not. For me, if you have another teacher, instructor, professor, you'd be sure you do what they want you to do. But the 0 between the decimal and the 2 is non-negotiable. It's decimal and then 0 and then 207. That 0 in between the decimal and the 2 is non-negotiable. All right? And so we have one more of these we want to transform into scientific notation. Decimal notation from scientific notation. I'm doing 4.6 times 10 to what? A negative exponent. That's going to get smaller. So I say 4.6, and then I say 1, 2, 3, 4, 5. And I draw my little arrow. That's where my new decimal goes, right? I got to add 1, 2, 3, 4 zeros. If you start in scientific notation and it's a negative exponent, you're going to add 1 less 0 than the absolute value of the power. There's 5 as the absolute value of the power. 4 zeros is what you added. So then here, this is going to be 0.000046. Or I could have written that with a 0 out front, but that doesn't change the fact I still have 4 zeros between the decimal and the 4. Those zeros are non-negotiable. They must be there. Must be there. Non-negotiable. Have to be there. So then, now let's go the other direction. We start with 456,000. Okay, not a real big number. I mean, honestly, some of the ones I did on the page before were better to write in decimal notation. We're just practicing going back and forth. But now this second number I have here, right? We got thousands, millions, billions, 540 billion there. That would be a little easier to write in scientific notation possibly, and especially if it gets even bigger than that. So here, first of all, if we want to change from decimal to scientific, decimal right now on 456,000 is at the end. Right? 456,000 is at the end. Well, where do I want to move the decimal? I want 1 digit to the left of it, and it can't be 0, so between the 4 and the 5. So then I'm going to take this decimal and move it 1, 2. Now look, I go to the comma, but I don't count the comma. I count the 0, right? That's the third one. 4th move and the 5th move. That moved 5 times, right? 1, 2, 3, 4, and 5 moves. It moved 5 times. So this is going to equal 4.56 times 10 to the 5th. Now, it's either going to be plus 5 or negative 5. And again, I don't get caught up in right and left. I want to go back and ask myself, what do I need to multiply 4.56 by to get 400 and something thousand? Does it need to be a positive 5 and be bigger, or a negative 5 and get smaller? It needs to be bigger, right? 4 point something has got to get bigger to be 400,000. So this is a positive 5. Okay? This has to be multiplied by something positive, bigger, to become this number here. All right, so let's look at the next one, 540 billion we decided, right? This is the thousands, this is the millions, this is the billions, right after you pass that. So we have here 540 billion. So where does the new decimal go? It's right here right now. it goes between the 5 and the 4. So we're going to say 1, 2, 3. Remember, we go to the comma, we just don't count the comma, right? We count that 0. Then we count the next 4, 5, 6, 7, 8, 9, 10, 11. So this is going to be 5.4 times 10, and we know there's an 11 here. Is it a plus 11 or a minus 11? Well, again, what do you multiply 5.4 by to get 540 billion? It's got to be positive. It's got to get bigger, right? So this is times 10 to the positive 11 power there. It's got to get larger or bigger. And then 0.00081, the decimal is visible here. We see it because we start with an actual decimal, meaning less, not necessarily less than 1, but something that goes out and has tenths, hundredths, thousandths, that kind of thing. So here it goes out. So where does the decimal go? Between the 8 and the 1. So we move it 1, 2, 3, 4. Okay, and again, the reason I don't get caught up in plus right and left, if you're moving the decimal right, this is going to be a negative exponent, and when you had the negative exponents on the page before, you moved it left. So that's why I don't get right and left. I talk about and rationalize with myself and reason out. I use reasoning, logic, and I say, am I making it bigger or smaller? And then that tells me if I use a positive or negative exponent. So here, this is going to now be 8.1. My decimal's a little high there. 8.1 times 10. How many places did I move it? 1, 2, 3, 4 places. So 10 to the 4th. Let me fix my 10 here. 10 to the 4th. And is it positive 4 or negative 4? Well, let's talk about this. 8.1. What do I multiply by this to get a little decimal here? It's got to go smaller. If it's smaller, that means I'm dividing, so I got to have a negative exponent, right? The negative exponent says, hey, put the 10 in the bottom and divide. But in scientific notation, and by the way, in the classes I teach right now currently, in my algebra classes, I should say, I should exclude anything above that. But in my algebra classes, I always want your answers with positive exponents except this. Scientific notation is the only time you can give me a negative exponent, and it's okay, all right, for the final answer in my algebra classes. So 8.1 times 10 to the negative 4 power. And it's negative 4 because 8.1 has got to get smaller to become 0.00081, to become that decimal. And then the last one on this page. What do I do here? Let's see. The new decimal needs to go where? You say between the 9 and the 0. Well, the 0 before the 9 or after the 9? That's right, after the 9. Okay? So there's the new decimal. So we move it 1, 2, 3, 4, 5, 6 places. So this is going to be 9.08 times 10, and we said 6, didn't we? 1, 2, 3, 4, 5, 6. Yep. So 10 to the 6 or 10 to the negative 6? Well, again, 9.08's got to get smaller to become that decimal, so it's a negative exponent there. A negative exponent. So there's your final answer there because it's got to get smaller. Negative exponent. And then as promised, the final 3 here where we actually do some multiplying and dividing with the scientific notation. You know how to multiply and divide exponents. You know how to multiply and divide numbers, real numbers. So we're just going to break it up, right? If you have one term, which a scientific notation is one term, because they're being multiplied, you have the number out front, in this case, the 3, and then you have the 10 to the 4th. So the 3 is the first factor, and the 10 to the 4th is the second factor. This is the same thing as having 3x to the 4th and 2x to the 7th, and multiplying that and getting 6x to the 4 plus 7. Right? We're going to do the same thing here with scientific notation. We're going to multiply the things out front, the 3 times the 2. So 3 times 2 gives me what? 6. And then times 10. Now we're going to multiply these together. What do we do when we multiply like bases? We add the exponents. So this is going to be 6 times 10 to the 11th. Now the big thing you want to check here is, does that fit M being between 1 and 10, including 1 but not including 10? Remember that one digit to the left of the decimal that can't be 0. That one digit to the left of the decimal that cannot be 0. And this fits the bill, so 6 times 10 to the 11th power. If that had something like 61 or 0.6, you'd have to adjust the decimal place and make it work. So look at the next one. 40 times 10 to the 20th divided by 20 times 10 to the 10th. Again, when you divide two things, if it's one term over one term, a monomial over a monomial, then you can divide out the things that are alike, the factors that are alike. So the 40 and the 20 are factors that are alike. 40 becomes a 2 and 20 becomes a 1, right? 20 goes into 40 twice. So this becomes 2 times 10. And when you divide these things like bases, what do you do to the exponents? You subtract them. And so in scientific notation, I'm not going to worry about is the top bigger than the bottom, the numerator bigger than the denominator, or whatever. I'm just going to do the numerator's power minus the denominator's power, the top's power minus the bottom's power. Every time, because in scientific notation, I said what? You can leave the answer with a negative exponent. You don't have to move it here. You have to move it every other time, but not here. So this is going to be 2 times 10 to the 10th power. And again, this fits the bill. One non-zero digit to the left of the decimal. So you're good. And then the last one, 6 times 10 to the 11th times 7 times 10 to the 23rd. This problem is just like the first one, except different numbers. So we're going to do the same thing. We're going to do 6 times 7, and then we're going to do these two things by adding the powers. So 6 times 7 is 42 times 10 to the 11 plus 23. Right, those are the exponents being added. So this is 42 times 10 to the 34th power. But wait a minute. The decimal's here, and we need to move it over to here, right? So we need to move the decimal place how many places? One place, right? So this becomes 4.2 times 10. And if I move it one place, then that 34 is going to either become what? 33 or 35. Now don't just guess and go, I have a 50-50 chance. Okay? Think about what's going on here. If I multiply this times this, and it's got to be the same thing as this times this, then what happened here? 42 got smaller to be 4.2, right? 42 got smaller, so that means this right here has to do what? Get bigger. So then this is going to be 10 to the 35th. Think about that. If the decimal starts here and I move it 34 places this way, if it starts here and move it 35, that's the same thing, isn't it? So I reasoned it out again, right? I used logic. I said, hey, if 42 got smaller to become 4.2, then my 10 to the power's got to get bigger to be the same number when I multiply them. And vice versa, if I had gone from 0.42 to 4.2, I got bigger, then the other side's got to get smaller. So just make sure you reason that out there and to sort that out and get your answer in scientific notation. If you had left it 42, then you have two digits that are not zero to the left of the decimal. You have to only have one digit there, and it can't be zero, or it's not in scientific notation. Hope this helps you out with scientific notation, mainly just back and forth between scientific and decimal, but then also if you multiply or divide them, just the little things to watch for here. This is the basics. You may need more and then that kind of thing. All right. So, but this is just, again, the basics to get you started with scientific notation.